This is problem 34, and this is a Bragg diffraction problem. A certain crystal has rows of atoms separated by 0.423 nanometers. A beam of electrons is accelerated through a potential difference of 250 volts and is incident on the crystal. We want to know what the wavelength of the electrons is. So, Bragg diffraction on page 3, and the equation for that is on page 4. So for Bragg diffraction, we have 2d sine theta is equal to n times the wavelength, where d is the distance between adjacent crystal planes. They told us in this problem that's 0.423 nanometers. And theta is the angle. I think that's something we're going to be looking for. And lambda is the wavelength. In this problem, in part A, they're asking us to find the wavelength of the electrons. And we were told that the electrons are accelerated through a potential difference of 250 volts. So remember that the change in kinetic energy is equal to Q times delta V. Delta V in this problem is 250. And so the change in kinetic energy is 250 electron volts, since the charge for the electron has a magnitude E. And assuming that the electrons are starting from rest, 250 electron volts is the final kinetic energy. And I can find the total energy by taking the rest energy and adding the kinetic energy to the rest energy. For electrons, we have 511 kilo electron volts. The 250 electron volts would be 0.250 kilo electron volts. So we have a total energy of 511.250 kilo electron volts. I need to find the wavelength. Okay, so if I can find the momentum, then I can find the wavelength. And I know E total squared is equal to mc squared plus pc squared. So I want pc, that is the square root of E total squared minus mc squared squared. E total is 511.250 kilo electron volts. mc squared is the rest energy of 511 kilo electron volts. And that gives us 15.986 kilo electron volts. Then I can find the wavelength by doing HC divided by PC. For HC, I can use either 1240 electron volt nanometers. So I have 1240 electron volt nanometers or 1240 mega electron volt femtometers. So let's use 1240 electron volt nanometers. And then we can write this as 15986 electron volts. And then we get 0.077566 nanometers. That's the wavelength that they wanted us to find for part A. Then in part B, they ask us at what angles from the crystal face will the interference maximum be found. So we use the formula for Bragg diffraction here. I'm looking for the angle, so I can rearrange this formula. First, bring the 2D over to the other side, and then take the inverse sine. So the angle is the inverse sine of n lambda over 2D. So let me put numbers in now. N is an integer, and that will tell you what maximum it is. And the wavelength is 0.07756 nanometers divided by 2D. D is the 0.423 that they gave us. Okay, and then they asked us at what angle. So this is similar to what we did at the very end of Physics 261 with single and double slit interference, or thin film interference. So if you give me 3 angles for this, I will be satisfied with that. Okay, so we can simplify this first, and this is n, your integer, times 0.09169. Okay, so first you can put in 1. When n is equal to 1, the angle is 5.26 degrees. When n is equal to 2, you get 10.57 degrees. And when n is equal to 3, we get 15.97 degrees, and we're going to stop there. So I will always be happy with the first 3 values. Okay, and then in part C, it says, if the beam is replaced with a beam of protons, what will the interference maxima be resolvable? Assume that if the maximum are separated by less than 1 degree, the individual maximum cannot be resolved. So we're going to do the same thing, but with protons. So the kinetic energy is still the same because, did I write it somewhere here? Yes, because the charge has the same absolute value for the protons. So what would change here is the mc squared. So for part C, we have E total is equal to, for protons, mc squared is 938.3 mega electron volts plus 0.250 kilo electron volts. Oh, I guess we'll write that as 0.00250 mega electron volts. So that gives us 938.300250 mega electron volts. And then we can find PC using the same formula that we had up here. PC is equal to 938.300250. Just remember it's in mega electron volts, and we'll leave the units out. Minus the rest energy, take the square root, and that gives us 0.6849 mega electron volts. And then we can find the wavelength using the de Broglie wavelength formula. Since this is in mega electron volts, we'll use 1240 mega electron volt femtometers divided by 0.6849 mega electron volts gives me 1810 femtometers. And then I can use the formula that I have here to write an expression for the angles. So this is n times the wavelength, which is 1810 femtometers. Femtometers is times 10 to the negative 12th. Then we divide that by 2 times d. D is the same as what we had up here. So that's 0.423 nanometers. So it's 10 to the negative 12th in the numerator and 10 to the negative 9th in the denominator. And if we take care of that, we get the inverse sign of n times 2140 times 10 to the negative 6th. And then putting in 1 for n, we get 0.1226 degrees. And if we put in 2, we get 0.2452 degrees. And they asked us for part C if the maximum are resolvable, and they would be resolvable. Oh, they would not be resolvable if they're separated by less than 1 degree. These are separated by less than 1 degree. So for part C, it's not resolvable. And that concludes problem 34.